In this episode on our series on indices, we will concentrate on the quotient law of indices. Welcome to Math with Truth. So we start off by looking at some examples that lead us naturally to deducing the quotient law of indices. And then by examples, we see how the zero index rule and negative index rule can be derived from the quotient law of indices. Then we solve several examples that enable you to build the skill and confidence that you need to solve indices problems. At the end, we have skills builder that helps you to further deepen the skills that you build from this video. So as usual, we start with the baby steps. Yeah, we start with solving questions of this kind and quickly solving several questions leading to this type of questions that we can solve. And that is how we build the skills gradually and making it possible for you to build skills that stick. Let's get started. So example 1, we have 2 exponent 3 divided by 2 exponent 2. How do we simplify this? So if we write that out fully, we have 2 times 2 times 2. And 2 exponent 2 is 2 times 2. Now, we can cancel out the common factors. We have 2 at the numerator and then 2 here in the denominator. They cancel out. We take another pair of 2's, they cancel out. And then we're left with only 1, 2. And that is 2 multiplying itself 1 time. So we have 2. The second example, we have 9 exponent 5 divided by 9 exponent 2. We have 9 times 9 times 9 times 9 times 9 divided by 9 times 9. And then we can cancel out the common factors between the two, and that is all. We've cancelled out those factors, leaving us only 3 of the factors, 3 of the 9's. So we have 9 multiplying itself 3 times. So we have 9 exponent 3. Then number 3, we have 5 exponent 6. So we write that out. Divided by 5 exponent 3. And then we cancel out the factors one after the other till we have no other factors to cancel between the denominator and the numerator. And then we see how many factors are left. Here we can see that we have 3 5's left. So we have 5 multiplying itself 3 times. And so that gives us 5 exponent 3. Example 4. We have 7 exponent 4. So we write that out. And then we write out 7 exponent 2. Then we cancel out those, and this gives us 7 exponent 2. Okay, now writing out 6 exponent 250 is just too much time consuming. So we want to do that like usual, as we did in the product law, as we did in the episode on the product law of indices. We're going to do the same thing here too. So what we do is we look at example 1 to 4 to derive a pattern. See, then we can use that as a rule or a law to solve the rest of the questions. So let's start with example 1. With example 1, we can see that we started off with 2 multiplying itself 3 times. And then we cancelled out the number of times that 2 is multiplying itself in the denominator. Okay, so basically what we did is 2 exponent 3, and then we cancelled out 2 exponent 2. So 2 multiplying itself 2 times. That's the number of factors in the denominator. So minus 2, and that gives us 2 exponent 1, which is 2. Let's look at example 2. We started off with 9 exponent 5 in the numerator, and then we cancelled out 2 of the 9's because the denominator is 9 exponent 2. And so that is cancelling out 2 9's from the numerator. So it means we subtracted 2 from the 5 that we started with, and then that gave us 9 exponent 3. Similarly, with example 3, we started off with 5 exponent 6 in the numerator. So here we have 5 exponent 6, and then we cancelled out 3 of them because in the denominator we have 5 exponent 3, meaning 5 multiplying itself 3 times. So we cancelled out 3 5's from the numerator, and that leaves us with 5 exponent 3. Again, in example 4, we started with 7 exponent 4, and then we cancelled out 2 of the 7's because the denominator is 7 times 7, and that leaves us with 7 exponent 2. So now we can start seeing the pattern, right? And so we're going to apply the same reasoning, the same pattern to example 5. Now here we will have 6 exponent 250 in the numerator, and then 6 exponent 100 in the denominator. So all those 106 in the denominator will be cancelled from the number of 6 in the numerator. So then we subtract that, and then we come up with 6 exponent 150, which is correct. So then, by inspection, by observation, we have come up with this rule. Yeah, let's try to formalize it. Let's try to write a general form of it. So in example 6, if you have a exponent n divided by a exponent m, what is it? What will it be? You can pause the video and write that out for me. Write it in the comment. So that will be a exponent n minus m. And this is called the quotient law of indices. Now, I want you to describe the quotient law of indices in your own words in the comment. Now, the quotient law of indices states that if you have an indices expression divided by another indices expression of the same base, then that is equal to the base exponent, the index of the numerator minus the index of the denominator. I will want you to intentionally state it that way, as the index of the numerator minus the index of the denominator. Sometimes it can be stated as the base exponent, the differences between the exponents. Well, that sometimes can be tricky for students if they really do not grasp the concept, you see. Because if you have, for instance, 2 exponent 6 divided by 2 exponent 4, then, of course, this you will say, well, the difference between the exponents 6 and 4 is 2, right? And you are likely to write 2 exponent 2. However, if we turn this to 4 and 6, and some students get it confused, they just find the difference between the exponents, which is 2, wrongly stated. So, but this intentionally stated as the base exponent the index of the numerator, which is 4, minus the index of the denominator, which is 6. And that gives you 2 exponent negative 2. Okay, that is the quotient law of indices. And state it intentionally. Okay, all right. Let's solve some problems. Example 7. X exponent 7 divided by x exponent 3. So x exponent 7 minus 3, 3 is equal to x exponent 4. Example 8. M exponent 4 divided by m exponent 7. Now this sign of this division sign can also be used. Okay, this is then the dividend and this is the divisor, which then means that you can write this as m exponent 4 divided by m exponent 7, which is equal to m exponent the index of the numerator minus the index of the denominator, which then gives you m exponent negative 3. Okay, take note of that. Intentionally stated that way. And so again, m exponent negative 3, when the exponent is negative, what does it mean? Well, we will get to know that in this lesson. So stick around. 10, example 9, we have a exponent 9 minus 5, which gives you a exponent 4. Another thing that we will get to know in this video is when we have indices expressions like this. We have t exponent 0, and we'll get to know what that means. But for now, let's just apply the quotient law that you have derived. So we have t exponent 0 minus 4, which then gives us t exponent negative 4. Example 11. When you have 2 exponent 3 divided by 2 exponent 3, that is equal to 2 exponent 3 minus 3, which then is equal to 2 exponent 0. Well, we also do know in basic arithmetics that if you have a number divide itself, that gives you 1. So 2 divided by 2 is 1. 10 divided by 10 is 1. Billion divided by a billion is 1. Okay, so then, well, arithmetic says that this should be equal to 1 because we have 2 exponent 3, which is 8. That's 2 times 2 times 2, 2 times 2, 4, 4 times 2, 8, divided by 2 exponent 3 should be 1. 8 divided by 8. We can also see this way that even if we expand this like we did for example 1, 2, 3, and 4, we have 2 times 2 times 2 divided by 2 times 2 times 2. And then we can cancel out the common factors. Okay, then this gives us 1 times 1 times 1, that is 1, divided by 1 times 1 times 1, that is 1, and that gives you 1. So then, which one is correct? Do we go with what we know from basic arithmetics, that any number divided by itself is 1? Do we go with indices, the quotient law of indices, that says that 2 exponent 3 divided by 2 exponent 3 is equal to 2 exponent 0? Or do we go with this expansion here that we can see also gives us 1? Which one should we go with? Well, both are correct. Actually, 2 exponent 0 is equal to 1. And that gives us some glimpse into what this means. Okay, let's look at it formally. So if we have a exponent n divided by a exponent n, that gives us a exponent n minus n, which is equal to a exponent 0. And that we also know by our arithmetics and by this expansion here, that is also equal to 1. Yeah, and this is what we call the zero index rule. And what does the zero index rule state? How can you describe it? Describe it in the comments. The zero index rule states that any number raised to the power 0 is equal to 1. When you raise a base, which is any number, to the power 0, that is equal to 1. So stated this way. Okay, so let's solve some questions. We have 13. This we know will be x exponent 7 minus 7, which is equal to x exponent 0. And by the zero index rule that you have derived, we know that that is equal to 1. Okay, what about this? Here we can see that this is equal to, by the quotient law of indices, we have 0 minus 5, which is equal to m exponent negative 5. And this is also equal to, now look at this, we can rewrite this one as 1 over m exponent 5. Okay, so take a look at this for me. Let's do another one. A exponent 0 divided by a exponent 10. This is equal to a exponent 0 minus 10, which is equal to a exponent negative 10. But this is also equal to a exponent 0 is 1 divided by a exponent 10. And we can also write this one as 1 over a exponent 10. Okay, are you beginning to see a pattern? Yeah, okay, let's do this one. Number 16, we have 1 divided by t exponent 4 is equal to, well, let's write this one so they can have the same base and we can apply the quotient law of indices. Yeah, so we have t exponent 0 divided by t exponent 4, and this is equal to t exponent 0 minus 4, applying the quotient law of indices, and that is equal to t exponent negative 4. Now, here we started from this one here, which is equal to 1 over t exponent 4. Take note of this one too. Have you seen a pattern develop? What will be a exponent negative 5? Can you write that in the comments? This will be equal to 1 over a exponent 5. Okay, so a exponent negative 10 is equal to 1 over a exponent 10. T exponent negative 4 is equal to 1 over t exponent 4. We can see by applying the quotient law that pattern begins to emerge. Then we can formalize it. We can make it general. We can have a general statement for it. And what will that be? If you have a exponent negative n, what will that be? This will give us 1 over a exponent n. Yeah. So this is what we call the negative index rule of indices. And what does that state? Can you pause the video and write it? Describe it in your own words in the comments. The negative index rule states that if you have any base raised to a negative index, that is equal to 1 over the base raised to a positive of the index. So if you have any number, could be 10 exponent negative 2, that is equal to 1 over the base, which is 10, raised to the positive of the index. The index is negative 2. The positive of that is 2. Okay. Now, this can be fully stated, however, in another way. So that can be stated as any number, exponent, and negative index is equal to the reciprocal of the number, that is 1 over the number, all exponents positive of the number of the index, or the index without the negative sign. This can be expanded as 1 exponent n over a exponent n, which then gives you 1 times itself, n times is 1. So you have 1 over a exponent n, which then brings you to this. Okay. However, stating it this way has an advantage when we come to looking at fractions with negative exponents. All right. So if you have 2 over 3, all exponents negative 4, what is it? So we will look at that when in a later video. For now, just state it this way. Know that we have a exponent negative n is equal to 1 over a exponent n. That is the negative index rule of indices. And we have derived it gradually from examples. And so it sticks with you. And that is how you should learn indices. So let's look at some examples. We have the product of two expressions in the numerator and the product of two expressions in the denominator. So then, since we have products of expressions, we have to use the product law of indices. And we covered the product law of indices in a previous video. I have provided a link to that video in the description of this one. So if you have not watched it, you can go and watch that one. And also, if you have not subscribed to this community, you're not part of this channel, you're not growing with us, then please subscribe to the channel, like the videos, and share them with friends so we can grow together as a community of people learning math. Okay. Now here we have the product law of indices states that if you have a exponent n times a exponent m, that is equal to a exponent n plus m. If you have the product of indices expressions of the same base, then that product is equal to the base exponent, the sum of their indices. Okay, so then we have a exponent n times a exponent m. Because the bases are the same, you maintain the base and then you sum the exponents. And we derived this in that video, how we came by this. So we just don't state the formula, we derive it gradually for you to see how it unfolds, like you did with the quotient law of indices. Okay, so you can check on that one. Okay, so applying this, we have x exponent 7 plus 3 divided by x exponent 3 plus 2. This gives us x exponent 10 divided by x exponent 5. And this, then, we can apply the quotient law of indices because the base are the same, and so we can retain the base. And we said that it is always the index of the numerator, that is 10, minus the index of the denominator, and that is 5. And that gives us x exponent 5. This one will be, we have the common base and the expressions are multiplying. So we apply the product law of indices and to the numerator. So we have a exponent -3 plus 6 divided by a exponent -1 plus 2, which then gives you a exponent 3 divided by a. And that is, then we can apply the quotient law of indices to this one. Remember that a has a exponent 1. We usually don't write that. So then this is equal to a, again, the exponent of the numerator minus the exponent of the denominator, which then gives you a squared. Okay, let's go on. So here we have a exponent 7, b exponent -2 divided by a exponent 3, b exponent -5. Now, this one we can see that, well, they don't have the same base, so we don't apply the product law of indices to the numerator or to the denominator. We don't do that. But we can see that the bases are the same here, so meaning we can apply the quotient law of indices. Then we rewrite it differently a bit, just to show you, just to make it clearer. We have a exponent 7. Let me write that well. A exponent 7 divided by a exponent 3 times b exponent -2 divided by b exponent -5. And this is equal to a exponent 7 minus 3, applying the quotient law of indices to this one, and then you apply the quotient law of indices here too. So b exponent -2 minus 5, and you should take good care when working with these things. The signs are very, very important. Okay, all right. So this then gives you a exponent here, 7 minus 3, that is 4, times b exponent -2 minus is plus 5. So -2 plus 5 gives you 3. And this is equal to a exponent 4, b exponent 3. Okay, now we proceed. Number 22. M exponent 0, n exponent 4 divided by n, m exponent -2. So here we can rearrange this a bit so it's going to align like this one did. So we have m exponent 0, n exponent 4 divided by m exponent -2 and n. Okay, now this we just working with or playing with the commutative property of multiplication. If you have a times b, this is equal to b times a. 2 times 3 is equal to 3 times 2, which all equal to 6. Okay, so we have not changed anything here by swapping their positions. Okay, so then when we arrange them that way, then it makes it more visible. Then we have m exponent 0, m exponent -2 times n exponent 4 and n. And this gives you m exponent 0 minus -2 times n exponent 4 minus, we do have some 1 here, we don't write it, and then we have 1. That gives you m exponent 0 minus minus, so 0 plus 2, which is 2, times n exponent 4 minus 1, which is 3. That is simplified. Then let's do this one, 23. So here we have some numbers. Well, for now, we can just cancel out the numbers, right? So 2 into itself, 1, 2 into 4, 2 times. So we have x exponent 5 divided by 2x exponent 2. All right. Now we have x exponent 5, so x, meaning we can apply the quotient law of indices, okay, to the expressions that are having x as their base. So then we have x exponent 5 minus 2 divided by 2. And this is equal to x exponent 3 divided by 2. Okay. Now let's do this. Again, here we just write x exponent 5. You can do it straight, minus 2 times y exponent 3 minus 1 is equal to x exponent 3 y exponent 2. Okay, so what you did is write out these ones. So like x exponent 5 divided by x exponent 2 times y exponent 3 divided by y. And then you do them individually like this. Okay, here we have to simplify the following to have only positive indices. Okay, another condition has been thrown in here. We are just not to simplify, but we have to simplify and not have negative indices in there. So then we don't want this negative indices in here. Okay, we have to simplify to get rid of the negative indices or exponents. So this one we have 3 here, 1, 3 here, 3. So we can write this as 3x exponent negative 2 y exponent 4 divided by x exponent 5 y exponent negative 1. Okay, then we write this one as 3x exponent. Now this and this, you can apply the quotient law of indices. So you have negative 2 minus 5, and y, you apply the quotient law of indices, that is 4 minus minus 1. Always be careful with that, okay? And this is equal to 3x exponent negative 2 minus 5, that is negative 7, and y exponent 4 minus minus 1, that is 4 plus 1, and that is 5. Now, we do not want this negative index. We don't want it. So we have to get rid of the negative 7. And that brings us to our knowledge of the negative index rule. That tells us that if you have a exponent negative n, that is equal to 1 over a exponent n. Okay, so instead of writing x exponent negative 7, we write this instead, 1 over x exponent 7. So then this can be 3 times 1 over x exponent 7 times y exponent 5, which we can write neatly as 3y exponent 5 divided by x exponent 7. And that is our answer. So here, well, a lot of things going on. But yeah, let's take it one step after the other and everything resolves naturally. By observation, you can see that there is A here, there's A there. Well, so we can rearrange them. We see that we have to resolve, we have to simplify that first. And meaning we have to apply the product law of indices first. And then we can apply that also to the denominator. We see C exponent 4 and C exponent -5 in the denominator. So then let's get started with it. We have A exponent -4 and A exponent 3, well, using the commutative property of multiplication. And then we have B exponent 6 and C exponent -2 divided by, we rearrange this one as well. Well, A exponent -5, and then we have B exponent -1, and we have C exponent 4 times C exponent -5. Okay, so we can apply the product law of indices to simplify this too. And then we have A exponent -4 plus 3, B exponent 6, C exponent -2 divided by A exponent -5, B exponent -1, C exponent 4 minus 5. Well, stated fully as 4 plus minus 5, which is 4 minus 5, you see. And this is equal to A exponent -4 plus 3, that is A exponent -1, B exponent 6, C exponent -2 divided by A exponent -5, B exponent -1, and then we have C exponent -1. Okay, we can simplify this further. Now, then we can see that we have A here, A there, B here, B there, C there, C here. And so we can apply the quotient law of indices. Okay, so we have this times that. So we can apply the quotient law. So we have A exponent -1 minus -5. Then we have B exponent 6 minus -1. And then we have C exponent -2 minus -1. Okay, so then I just want you to get used to that. Always pay attention to the minus sign in the denominator. Always pay attention to that when you are applying the quotient law of indices. So then here we have A exponent 4, that is -1 plus 5, that is 4. And then B exponent 6 plus 1, that is 7. And then C exponent -2 plus 1, that is -1. Now, we do not want minus, like we want only positive indices. So we want only positive indices. We have to change that to a positive index. And so then that's what we're going to do. And we can do that by using the negative index rule of indices. And so then here we have A exponent 4, B exponent 7, B times 1 over C exponent 1, which we really don't write. And that is equal to, we can write this one nicely as A exponent 4, B exponent 7 divided by C. That's a simplified form of this. Okay, let's do this one. 27. Now, here you can see fractions as indices, right? Or the powers or the exponents. There is a deeper meaning, but we reserve that for later videos where you'll see that systematically, gradually, and also understand them very well. But for now, we just treat them like any other index and work with them. Okay, so here we have a exponent 7 over 2 divided by a exponent 1 over 2 times b exponent negative 3 over b exponent negative 6. And we can write this as a exponent 7 over 2 minus 1 over 2, that's applying the quotient law of indices, and then b exponent negative 3 minus 6, which gives you here is, well, since the denominators are the same, we retain the denominator, and then we have, the denominator of these two fractions. That's 2. We retain the 2, and then we subtract the numerators. So 7 minus 1 is 6 times b exponent negative 3 minus 6. That's negative 3 plus 6. So that gives you 3. And here we can simplify this. 6 over 2 is 3. So a exponent 3, b exponent 3. Now, this we can simplify even further using the power of product rule, which we will derive in later videos. And that is why we will strongly recommend that you subscribe to the channel. All right, so this, by the power of products, we can state this as a b exponent 3. We will discuss this in a later video. Okay, all right. So here we have this to simplify. Well, there is a number here, 1. There is here 12. And so we write this out. That is 12 a exponent 6 b exponent negative 4 divided by a exponent negative 4 b exponent 5. Well, this we can write as 12 times a exponent 6 divided by a exponent negative 4 times b exponent negative 4 divided by b exponent 5. And this gives you 12, then a exponent 6 minus 4 times b exponent negative 4 minus 5. And that gives you 12 a exponent 10 b exponent negative 9. Well, we don't want a negative index, do we? So we use the negative index rule to get it to positive, right? A exponent negative n is equal to 1 over a exponent n. So let's do that. So that would be 12 a exponent 10 b exponent negative 9. Let's write it here. And then we have 12 a exponent 10 times 1 over b exponent 9, which is equal to 12 a exponent 10 over b exponent 9. Let's simplify this one. So here we have x exponent 3 over 4. Here we can apply the rule here, minus 1 over 2 times y exponent negative 4 minus 5. Now, 1 over 2, we can also state 1 over 2. The equivalent fraction for 1 over 2 is the same as 2 over 4. So we have the same denominator to work with, all right? So then we can state this one differently here as 2 over 4. And so we have x exponent, since the denominators are the same, we retain the denominator. And then we have 3 minus 2, which is 1. And here we have y exponent negative 4 minus 5, which is negative 4 plus 5, which is 1. And that is equal to x exponent 1 over 4 y. Or we can state it as y x exponent 1 over 4. Number 30. 2 into 2 one time, and 2 into 8 four times. So, and we also see that we have t here, t there, meaning we have some rearrangement to do. So we apply the product law of indices, and then we also have some rearrangement here to do. We have p exponent -4, p exponent 3 in the denominator. And so we rewrite this once. We have p exponent -3, then we have t exponent 5, and then t exponent -3, then we have q exponent 4. All this divided by 4 times, well, let's write the p's, yeah? So p exponent -4 and p exponent 3, let's then write the t exponent -2, and then q exponent -2. So that is equal to t exponent -3, t exponent 5 plus -3, and then you have q exponent 4, all divided by 4 times p exponent -4 plus 3, and t exponent -2, q exponent -2. Then we can simplify this as p exponent -3, t exponent 5 minus 3, that is 2, and q exponent 4 divided by 4 times p exponent -4 plus 3, that is -1, and then t exponent -2, and q exponent -2. Okay, now we can apply the quotient law of indices. Yeah, so we have p exponent -3 minus -1, t exponent 2 minus -2, q exponent 4 minus -2 divided by 4. And this is equal to p exponent -3 plus 1 is -2, t exponent -2 plus 2, that is -2 plus 2, is t exponent 4, and q exponent 4 minus -2 is 4 plus 6, that is q exponent 6, all divided by 4. But again, we only want positive index, so we eliminate this negative index from there by applying the negative index rule. And that is equal to 1 over p2 times t exponent 4 q exponent 6 all over 4, which can be more nicely written as t exponent 4 q exponent 6 divided by 4p exponent 2. Number 31. Now, these examples, you are to find a number, okay, usually in the index, and sometimes it can also be the base. But let's solve this one for a number, a missing number in the index. So we are to find the value of n. Let's do some simplification here, since we can see that there is 2 here, 2 there, 2 expressions of the same base multiplying each other, meaning we can apply the product law of indices to simplify that. Okay, and so let's do that. We apply the product law of indices to this, and we have 2 exponent 3 plus n minus 1 divided by 2 exponent 2n minus 4 is equal to 2 exponent 5. Now we can apply the the quotient law of indices. Since we have these two bases are the same, we can apply the quotient law of indices. And the quotient law of indices states that if you have two here, the common basis, exponent, the index of the numerator, that is this one, 3 plus n minus 1, which is 3 minus 1, that is 2, plus n, minus the index of the denominator, that is 2n minus 4. And that should give you 2 exponent 5. Now, if you have two indices expressions that are equal, if the bases are the same, then the exponents should also be the same. That is, if you have a exponent n is equal to a exponent b, if they are equal and the bases are the same, then the exponents should be equal. Okay, so you have n is equal to b. Since the bases are the same, we can then write or equate the exponents. So we have 2 plus n minus 2n minus 4 is equal to 5. And here we have 2 plus n minus 2n minus 4 is equal to 5. So we write this out. Oh, wait a bit. See, now minus 2n minus 4 should give you plus 4. Now, again, that is where you have to slow down, take your time so you don't make that mistake. Okay? Always remember it. Remember this moment and always remember that when you have negative here and it's multiplying a bracket, you take your time and look for negative multiplying negative. Very important. Okay, now let's continue. We have um, 2 plus 4, that gives us 6. And then n minus 2n, that gives us minus n is equal to 5. Now, this is linear equation that you can solve. So here we can add n to both sides. So if we add n to both sides, we just want to eliminate this n, okay? And then we add n here. So we have 6 is equal to 5 plus n. Then we subtract 5 from both sides. So then we take this 5 away from here, leaving only n. And then we have 6 minus 5 is equal to 1. So 6 minus 5 is equal to n. And so this is 1 is equal to n, or n is equal to 1. Now, in exam conditions, when you have the time, and if you learn with us, be sure you have the speed to have the time to do so. You can verify your answers, okay? So let's verify if this is correct. So then we get this value back into this equation. What we're trying to say is that this value of n is what makes this equation true. So let's see if that is the case. So we have 2 exponent 3 times 2 exponent 1 minus 1, okay, divided by 2 exponent 2 times 1 minus 4. And that gives you 2 exponent 3 times 2 exponent 0, which is 1, divided by 2 exponent, this is 2 minus 4, which gives you minus 2. Now we can apply the quotient law of indices, can't we? We have 2 exponent 3 minus, watch out, minus 2, which then gives you 2 exponent 5. And that is what we have here. And so our answer is correct. Let's go to example 32. I will recommend you pause and then solve this one. Okay, let's do it together. Since we have 3 multiplying these two expressions multiplying each other, we have to apply the product law of indices to simplify it. And then we do the same thing for the denominator here as well. And then after we can apply the quotient law of indices to simplify further till we get to a point where we have a base raised to a certain expression is equal to the same base raised to another expression, and then we equate the index. Okay, so then let's get started. We have 3 here. We have 3 exponent x plus 2 plus 3 minus 1. Oh, wait, plus x minus 1 divided by 3 exponent 2x minus 4 plus 2x is equal to this. Here you have the same base and you have some exponents here, so you can just apply the quotient law of indices straight, and that is 3, which is the base, exponent the index of the numerator, that is 3x, minus the index of the denominator, that is 10. Okay, let's simplify this one. We have 3 exponent x plus x, that is 2x, 2 minus 1, that is plus 1, divided by 3 exponent 2x plus 2x, that is 4x, minus 4 is equal to 3 exponent 3x minus 10. Now then, we have x, we have 3, and so we can apply the quotient law of indices because the bases are the same and they are dividing each other. So we have 3, we maintain the base, exponent, the index of the numerator, that is 2x plus 1, minus the index of the denominator, that is 4x minus 4 is equal to 3 exponent 3x minus 10. Since we have equal base, we can just equate the indices. Okay, and so we have 2x plus 1 minus, now here again we have minus 4x, and negative, that's plus 4 is equal to 3x minus 10. And so here you have 1 plus 4, that is 5, 2 minus 2x minus 4x, that is minus 2x, is equal to 3x minus 10. Add 2x to both sides. So we have plus 2x plus 2x, and then you also add 10 to both sides. So plus 10 plus 10. So then this eliminates this from here, and this one eliminates the 10 from there. Okay, solving linear equations. So then here we have 5 plus 10 is equal to 3x plus 2x, which then is equal to 15 equals 5x. So here we divide by the coefficient of x. That's the variable that we're looking for. And then that gives you 5 here. 5 into 15 3 times. And so x is equal to 3. That is our answer. You can pause the video and try to verify if that answer is correct. So here you can do that verification. For instance, by substituting 3 into this expression here, this equation right here. So let's do that. Let's squeeze that one right here. So we have 3 exponent 3 plus 2, that is 5, times 3 exponent 3 minus 1, that is 2, divided by 3 exponent 2x, that is 6, minus 4, that is 2, times 3 exponent 2x, that is 6. Okay, and that is equal to 3 exponent 3x, that is 9, divided by 3 exponent 10. Now let's see. If we apply the product law to 3 exponent 5 times 3 exponent 2, that gives us 3 exponent 7, 5 plus 2. Yeah, and then we have 3 exponent 2 times 3 exponent 6. We apply the product law, that gives us 3 exponent 8. And this we can apply the quotient law of indices, right? And this is equal to 3 exponent 7 minus 8, which is equal to 3 exponent negative 1. Okay, now look at this one too. If we apply the quotient law to this, we have 3 exponent 9 minus 10, which is also equal to 3 exponent negative 1. So then, since the left side and the right side of the equation are equal, then it means that our answer satisfies this equation. Okay, all right. Now we have these questions, skill builder. You are to work out this one independently, and then we have another video that explains this, that walks you through these examples. Look at where we started from, baby steps, and this is where you are. You're able to solve these questions, and that is a great improvement. That is a great move that you have made in your understanding of indices and your confidence to solve complex indices problems. And so we advise that you do this one independently and then watch out for that video that explains this one, that tutorial. And so here we take a quick summary. We have the quotient law of indices that we deduced from examples, that if you have a exponent n over a exponent m, this is equal to a exponent n minus m. Always remember, it is the index of the numerator minus the index of the denominator. Then we have the zero index rule, which tells us that a exponent 0, any number exponent 0 is equal to 1. And then we have the negative index rule, which tells us that a exponent negative n is equal to 1 over a exponent n. Or we can state this as the reciprocal of the number, that is 1 over the number, all exponent n. That's the positive of the negative index. All right. And we solved a lot of problems, and you have the skills builder to work with. And so I will see you in the next video. However, in the meantime, if you have not subscribed to the channel, you are not part of the community, we welcome you. That you should subscribe to this channel, like our videos, and share them with friends. Hit the notification bell so when we upload other videos, you have access to them. We believe so strongly in SDG4, quality education for all. So we're doing our best to get mathematics education, free mathematics tuition to everyone around the world. And so help us achieve that dream, helping SDG4. Thank you, and see you in the next video. Stay blessed.